This is chapter 5, section 1. We're going to talk about verifying trig identities. And when we talk about verifying trig identities, we're providing the proof, okay? And in order to remember our fundamental trig identities, remember we have our reciprocal identities. Cosecant is 1 over sine. One that's not written here would be sine of x is equal to 1 over cosecant. So the reverse of that. Secant of x is equal to 1 over cosine of x, or I could write cosine of x is equal to 1 over the secant of x. Cotangent of x is equal to 1 over the tan of x, or we can write tan is equal to 1 over cotangent. These are also known as your quotient identities. The tan of x is equal to sine over cosine, and cotangent is cosine over sine. And then we have our Pythagorean identities. Sine squared plus cosine squared is equal to 1. Tan squared plus 1 is equal to secant squared. And then we have 1 plus cotangent squared is equal to cosecant squared. We have our even odd identities. Here's an odd function. Here's an even function. And tangent is an odd function. We have cofunctions. Remember, pi over 2 is 90 degrees. So if I have sine of 90 minus some angle, that's going to be equal to cosine of whatever that angle is. Or the output is completely equal to it. The same is true for tangent, cotangent are cofunctions, secant, cosecant, and then I can go in the reverse. Cosine, sine, cotangent, tangent, cosecant, secant. So now I'm going to incorporate all of these identities to provide proofs. Here's our first example. Alright, so let's take a look at example number 1. In this first example, it says use the given values to find the values of the 6 trig functions. Okay, here's telling me that sine's negative. So I know sine's only negative in quadrants 3 and 4. Because this is coming out positive, remember here, the first step to do is identify, are they giving you any of those identities we just looked at? Okay. Alright, so from here I need to identify which of these identities were we talking about. And notice that it's actually a co-function that we're referring to. Here I know I have sine of pi over 2 minus u is equal to cosine of u. So whatever's going on here is equal to cosine of that angle. So what this is telling us is this is cosine. Okay? However, I want proof. Okay, so it's not just enough saying, yes, this is true, cosine of it's x, not, I was going to write theta. Cosine of x is equal to 12 over 13. I want to provide proof. Well, how can I provide proof? Another way to provide proof of the following is to use the Pythagorean identity. Okay, so let's use the Pythagorean identity here. So we're told that this is sine, and I want to look for cosine. So, apologize. This is sine, I'm going to square it, plus cosine squared, let's call it theta, equals 1. So now I want to isolate cosine. I'm going to subtract this from both sides. So cosine squared theta equals 1 minus negative 5 over 13 squared. And then I'm going to take the square root on both sides. So I'm going to get cosine of theta is equal to the square root of 1 minus whatever this is. Well, let's go ahead and simplify the radical. This is going to be 1 minus 25 over 169. And when I take the difference, 169 minus 25, we're going to get 144 over 169. 144, take the square root of that is 12. 169, take the square root of that is 13. So notice that we end up with the same solution as what was out here, but this is the actual proof of cosine being 12 over 13. Alright, when we're providing proofs, another way to provide proof of this would literally be to say the cofunction that's allowing us to do the arithmetic of sine pi over 2 minus u is equal to cosine of u. from here, because of this, then cosine of u is equal to 12 over 13. So you could hypothetically give me that for the solution of cosine of, here it's x, I was writing u because that's what was in here. Or you can provide the Pythagorean identity and give me the solution for cosine. So you can't just write cosine equals 12 over 13. I want to see some kind of proof. What is allowing you to get to cosine is equal to that value? Okay? Cofunction allows us to do this. The Pythagorean identity allows us to do this. And now I'm going to use reciprocal and quotient identities to find the rest. So let's actually go ahead and continue from cosine. I know that secant, I'm going to write x because the given was x, is equal to 1 over the cosine of x. Therefore, our solution for secant of x is equal to 13 over 12. So you see I'm providing the identity and then I'm providing the solution. That's verifying the trig identities. Okay? Then I'm going to do the same thing with sine. Sine was given to us. They gave us negative 5 over 13. And now I'm interested in the reciprocal here. That's going to be cosecant is equal to 1 over sine. And now I'm allowed to flip it over. So here cosecant is equal to negative 13 over 5. And now I want the quotient identities for tangent. Tangent is equal to sine over cosine. Therefore, I'm going to take sine, put it over cosine, which what do we get for cosine, guys? 12 over 13. And my 13s are going to reduce, and my answer here is negative 5 over 12. From here, I can use cotangent with the reciprocal or cotangent with quotient identity. Okay, let me just zoom in and show you what I mean. It's up here. Tangent with a reciprocal identity with this one. Tangent with a quotient identity would be this one. Oops, I'm moving the wrong thing. Yes, you have to find all 6 trig functions. So here I'm going to just use cotangent of x is equal to 1 over tan. So now I can flip over tangent. So I'm showing you how I'm getting what. Okay, so it's really important to write your identity first and then write your solution. Okay, so here's example number 2. We're going to use trig identities to simplify the given expression as much as possible. So the first thing I want to do is begin writing everything, if you can, in terms of cosine. And if you have sine in there, you want to write things in terms of sine. So always kind of do that as step 1. Can you re-express it in terms of sine and cosine, and then go from there? So this is going to become 1 over cosine of x because of the reciprocal identities. And then the next thing I want to do here is distribute that cosine that's on the outside. So I'm going to distribute it to both those terms. And notice that I'm writing each step out. When you're verifying any type of identity, you need to show it step by step because it is a proof. Well, cosine over cosine, that reduces to 1. And this is a Pythagorean identity. Let me show you. The one that was manipulated was this one. Because what happened was, remember, we had 1 minus cosine. So what happened, this was subtracted from both sides, and we end up with sine squared u is equal to 1 minus cosine squared u. So if this is what we had in our proof, what is that equal to? That's equal to sine squared theta, sine squared u, sine squared x. However you want to rewrite that, I'm okay. So this, oops, I meant to circle that, is equal to sine squared x. And now it's simplified. Alright, so let's take a look at example number 3. Remember, before we start actually verifying equations, what we're going to do is simplify trig expressions. So one of those concepts that we need to know very, very well is how to factor a trig expression. So when we talk about something that looks like this, it might be a good idea to temporarily just take this sine squared x and re-express it using a variable. So maybe if I rewrite this as 3x squared, where x squared is sine squared x, minus 5x minus 2, and then consider factoring that. Go back to Algebra 1, Algebra 2 concepts and see, can you break this down? And then when you're done, just substitute sine of x back into x. And the answer is yes, this is factorable. I know that 3x times x is going to give me 3x squared. And I know that 2 times 1 is going to give me my 2. When I do my outer term, 3x times 2 is going to give me 6. And this is going to give me 1. I want my middle term to be negative 5. So therefore, I want that to be negative 6 when I distribute that 3x to that negative 2. And I want this to be plus 1x, so that way I get the middle term of negative 5. So just a quick check, you can always do this. And I know that when I add those two things together, I'm going to get negative 5x. So I did that right. I have my first term, my middle term, and my third term correct to this trinomial. Well, that's not our final answer, because remember, we started with a trig expression. So now what I want to do is just substitute wherever I had an x, plug the sign back in. So 3 sine x plus 1 times sine x minus 2. And just for this particular example, this is where we're going to stop. Because it's an expression, it's not an equation, we can't continue. If this was an equation, we can technically set each binomial equal to 0 and then solve. But we're going to do that in a different lesson, not in this particular lesson. Alright, example number 4 says perform the multiplication and use the fundamental identities to simplify. So here when we're performing the multiplication, basically this is a binomial that we're multiplying to itself. Then I'm going to distribute my first term, and I'm going to get sine of x times sine of x is going to give me sine squared x. That's my first term. When I multiply my second term, I'm going to get sine of x times cosine of x. Then when I start moving towards my middle term, I'm going to get another sine of x, cosine of x. And when I do my last term, I'm going to get plus cosine squared x. Now I want to draw your attention to right here. Whenever you have sine squared x plus cosine squared x, that's 1. It can't be sine of x plus cosine of x. It has to be sine squared x plus cosine squared x. That equals 1. And even if I had sine squared x minus cosine squared x, that is not equal to 1. The Pythagorean identity is this equals to 1. I can't tell you how many times I've seen that mistake where people just substitute a Pythagorean identity where 1 it does not exist. So here we do have a Pythagorean identity where I pointed from here to here, that's 1. And then we're going to join these two. Those are like terms, so I'm going to join them. I have 2 of those. So I have 2 sine x, cosine x. It's okay if you stop right here. I haven't introduced double angle formula, because this technically reduces a little bit further, but we're not there yet. I haven't introduced that particular identity just yet. So let's stop here for this particular example. Alright, example number 5 says use the fundamental identities to simplify the expression. Again, we start off just by simplifying, and very soon we're going to start verifying. But in order to verify, we need to know these fundamental trig identities very, very well. So I want to simplify everything as much as I can. If possible, always, whenever you're simplifying, try to re-express everything in terms of sine and cosine. Alright, so cotangent is cosine over sine. And secant is 1 over cosine. And now I can see that these two reduce, and I have 1 over the sine of theta. And now I can clearly see that I have a reciprocal identity. And here I get cosecant of theta. Alright, so we're simplifying this one as well. Here's where I need to know my identities very, very well. Here, I have a Pythagorean identity, and I have one here too. I just have a Pythagorean identity that's been manipulated. Let me show you. Alright, so if we look over here at our Pythagorean identities, remember what we're looking at is 1 minus sine squared theta. So that has to be this Pythagorean identity. Well, if I subtract sine squared theta from both sides, I end up with cosine. You put u, theta, I don't care what you put, sine squared u. So here you can actually see that 1 minus sine squared u or theta is equal to cosine squared u or theta. So that's a direct substitution up here. That's equal to cosine squared x. I want to draw your attention to the bottom because we have something similar happening down here as well. So down there, let's take a look. I have this one here. So what is cosecant squared theta equal to? Cotangent. So notice that you have to subtract 1 from this Pythagorean identity in order to get this. So this must be equal to cotangent. So over cotangent squared x. Okay. So now that I have that, let's re-express that over here. We have cosine squared x over cotangent squared x. This simplifies a little bit more. I'm going to re-express this cotangent as cosine over sine, and then I'm also going to remember that we're dividing fractions here. Cosine squared x over sine squared x. So now that I have that, I'm going to do state change flip. And then I can see that my cosines reduce, and my final answer is sine squared x. And now that's simplified. Alright, another example. It says to rewrite the expression so that it is not in fractional form. So I want you to think back. And I want you to think back to complex numbers. That's when we used I. And if we were trying to get rid of I in the denominator, what do we multiply the top and bottom by? So I'm going to multiply the top and bottom by the conjugate pair. So I'm going to multiply the top and bottom by 1 plus cosine y. Now when I do that, because these are conjugate pairs, the middle terms are going to reduce, so I only need to distribute the first term and the last term 1 times 1 and negative cosine times cosine. So let's rewrite it. And I'm purposely not distributing the numerator. And I'm going to show you why in just a second. So this is 1 minus cosine squared y. Now I want you to think back to those properties that I've been showing you all along and tell me, is this equal to anything else? Yes, the denominator is a Pythagorean identity, so I'm going to go ahead and I'm going to substitute. Here we get sine squared y, 1 plus cosine y over sine squared y. And now I can clearly see why I did not distribute that sine squared y in the numerator, because here it's going to reduce. You kind of want to hang out with the pieces just for a little bit to see, will anything reduce? If I had that distributed, I wouldn't have been able to create this move. And then notice that your final answer is 1 plus cosine y. So we were able to get rid of that fraction. Alright, so here's some examples from your textbook. This is number 21 and 25 from your text. It says factoring trig expression in exercise 21 through 28. Factor expression and use of fundamental identities to simplify. There's more than one correct form of each answer. So let's start with 21. Let's put 25 off to the side. And let's take a look at 21. 21, what I want to do is I want to factor out a tangent because that's consistent on both of these terms. So I'm going to factor out tan squared x, and And that's going to give me 1 minus sine squared x. Can we identify anything that's from our identities in this? Good, I have a Pythagorean identity. Right here I have 1 minus sine squared x, and that's equal to cosine squared x. Is there anything else I could substitute here? Good, tangent is sine over cosine. And does anything else reduce here? Yes, the cosines reduce, and our answer is sine squared x. Alright, so let's take a look at number 25. If it helps you, temporarily re-express it with variables, algebraic variables. So let's just rewrite this as 1 minus 2x squared plus x to the fourth. And ask yourself, is that factorable? If it is, factor it, and then re-express x to cosine. If it helps you, put this in descending power with x to the fourth first. Okay, yes, this is factorable. Here, we would end up with x squared minus 1 times x squared minus 1. So now what I'm going to do is wherever I had an x, I'm going to put cosine. So the given is equivalent to cosine squared x minus 1 cosine squared x minus 1. And ask yourself, can you substitute anything in here with a Pythagorean identity? So yes, a Pythagorean identity that has been manipulated is what's happening in these parentheses. However, it's negative sine squared x. And now when I multiply them together, I'm going to get positive sine 4x. And that's our answer.